All right, let's talk about one of the absolute cornerstones of machine learning, linear regression. Now, I know what you might be thinking. Linear regression sounds kind of basic, right? Well, stick around because we're going to show you how this seemingly simple idea is actually the hidden engine behind a ton of modern AI. Okay, so here's the game plan. First, we'll cover why these models even matter. Then, we'll get into what linear regression actually is. We'll peek under the hood at the math, talk about what happens when things go wrong, and wrap up with how to build these things the right way. So Section 1, why should we even care about linear models? You know, it's a fair question. It sounds like something you'd hear about in a Stats 101 class. But trust me, linear does not mean simple or outdated. Not by a long shot. And here's why. The versatility is just kind of mind-blowing. Yeah, sure, they're fantastic for predicting things like prices. That's regression. But you can tweak the same fundamental ideas to sort data into buckets, classification, or even to shrink down huge data sets. But here's the real kicker, that last point. Deep down, those giant, complex neural networks you hear about, they're basically just layers and layers of linear models stacked on top of each other. It's the fundamental building block of almost everything. All right, let's get into the nitty-gritty. What exactly is linear regression? It all starts with just understanding the regression part of the name. So regression, in simple terms, is all about prediction. We're trying to predict a number. Think about it like this. You have a bunch of information about a house. Its size, how many bedrooms, its location. Those are your input features. The goal of regression is to use that info to predict a continuous number, like what's the final sale price going to be? Okay, and here's the core philosophy behind it all. We assume that every piece of data we see, let's call it Y, is really made of two parts. There's the real predictable pattern, the signal, which we call f of x. And then there's, well, just random junk, noise. That little epsilon symbol there, that's the noise. It could be measurement errors or just random chance. The whole game, the entire point of building a model, is to separate that beautiful, clean signal from all the messy noise. And this is where the linear part of linear regression finally clicks into place. We make a big but super useful assumption. We say, you know what? Let's assume that underlying pattern, that signal, is just a straight line. It's not some wild, crazy curve. It's a simple, weighted sum of our inputs. The model's job is just to figure out the right weights for each feature, to draw the best possible straight line through our data. Okay, that's the big idea. But how do we actually find that perfect line? I mean, if you've got a scatter plot of data, there are literally infinite lines you could draw through it. How in the world do we pick the one that's the best? Well, first we need a way to keep score, right? We need some kind of mathematical ruler that can measure every possible line and tell us exactly how good, or more accurately, how bad it is. We call this a loss function or an error function. It basically just gives us a single number that says, this is how wrong you are. And the most common way to do this, by far, is something called mean squared error, or MSE. It sounds complicated, but the idea is actually pretty straightforward. For every single data point, you measure how far away it is from your line. That's your error. Then you square that error. Why square it? Well, it does two things. It makes all the errors positive, and it really punishes the big mistakes. A tiny miss doesn't count for much, but a huge miss gets penalized heavily. Finally, you just average up all those squared errors, and boom, the best line is the one with the lowest possible score. And now for the magic trick. This is what makes linear regression so cool. For a lot of other machine learning models, you have to kind of guess and check over and over to find the best answer, but not here. Thanks to the power of calculus, there is a single, beautiful formula. It's called the normal equation that just gives you the answer. You plug in your data, and it spits out the perfect set of weights, that's the omega symbol, that minimizes the error. It's a direct, one-shot solution, no guessing required. And if you thought that was cool, it gets even better. There's this famous theorem, the Gauss-Markov theorem, that basically gives this formula a gold star. It says that as long as the noise in our data follows a few simple common sense rules, like it's truly random and not biased, then this formula gives you what's called the best linear unbiased estimator, or BLUE. That's a fancy way of saying it is mathematically the best possible linear model you can build, period. But you knew there was a but coming, right? Life is messy. The real world doesn't always play by our nice, clean mathematical rules. So what happens when those assumptions break down? Well, that beautiful, elegant formula, it can go horribly wrong. So where does it break? The biggest problem happens when our input features are telling us the same thing. they're redundant. Imagine you're trying to predict someone's salary, and you use both their age and their years of work experience as inputs. Those two things are super correlated, right? This problem has a name, multicollinearity, and mathematically, it makes that tricky matrix inversion part of our formula, the XTX inverse bit, totally blow up. It becomes unstable. And this is what that instability looks like in practice. It's super weird. The model's overall predictions might actually still be pretty decent, but when you look at the individual weights for the features, they're complete nonsense. Look at this example. The model assigns a massive positive weight to years of experience and a massive negative weight to age. They're basically fighting each other and canceling each other out to get to the right answer. At this point, you just can't trust the model's explanation of why it's making its predictions. So how do we fix this? We use a brilliant technique called regularization. Think of it like putting a leash on your model's weights. The core idea is that we change the rules of the game. We tell the model, hey, your job isn't just to minimize the error. Your job is to minimize the error while also keeping your weights as small as possible. We add a penalty right into the scoring system for any weight that gets too big. And there are two main ways to do this. The first is called L2, or ridge regression. It penalizes the square of the weights. This has the effect of shrinking all the weights down, making the whole model more stable and less crazy. The second is L1, or lasso regression. It penalizes the absolute value of the weights. And this has a really cool side effect. It can actually force the weights of the least important features to go all the way down to exactly 0. So it doesn't just stabilize the model, it actually cleans it up by doing feature selection for you automatically. Super powerful stuff. Okay, so we've got the theory down, we even have a fix for when things get weird. Now for maybe the most important part, how do we actually build one of these things like a pro? How do you create a model that you can actually rely on? First things first, we need to get a key piece of vocabulary straight, parameters versus hyperparameters. Think of it this way. Parameters, like our model's weights, are the things the model learns by itself from looking at the data. But hyperparameters are the knobs and dials we have to set before the learning even starts. That regularization strength we just talked about, that's a classic hyperparameter. We have to decide how strong that leash should be. And this leads us to the single biggest trap in all of machine learning. You cannot tune those knobs and then test your model on the same data. That's like getting the answers to the test before you take it. To do it right, to avoid just fooling yourself, you have to split your data into 3 separate sets. You use the training set to let the model learn its parameters, use a totally separate validation set to fiddle with your hyperparameters and pick the best settings, and then, only when you've locked everything down and you're totally hands-off, you break out the test set for a final, honest grade on data the model has never, ever seen. Why go to all this trouble? Because it helps us solve this fundamental problem called the bias-variance trade-off. Look at the chart. If your model is too simple, that's high bias, it just won't be accurate. It underfits the data. But if your model gets too complicated, it starts to just memorize the training data, noise and all. That's high variance, or overfitting. It'll seem perfect on the data it's seen, but it will completely fall apart on new stuff. Our whole goal with that train, validate, test process is to find that perfect sweet spot right at the bottom of the U-curve, where the model is just complex enough, but no more. Okay, let's wrap this up. What are the big things to remember? First, linear models are the absolute foundation of machine learning, way more powerful than they sound. Second, linear regression is all about finding the best fit line by minimizing some kind of error score. Third, watch out, because that perfect mathematical solution can be unstable and regularization is your best friend for fixing it. And finally, and I can't say this enough, always use a train, validate, and test split. It's the only way to know if your model is actually any good. And that's our look at linear regression, from the core idea to building it right. So I'll leave you with one final question to think about. We spend all this time worrying about balance, right? Bias versus variance, simplicity versus complexity. But imagine a world where you had infinite data and infinite computing power. Would we even need to worry about any of that? Or is the entire challenge of machine learning less about the fancy math and more about the art of being smart with what little we have? Something to chew on. Thanks for joining us.